Hello class. In today's lesson I'm going to show you an example of how to use fundamental identities to simplify trigonometric expressions. So I'm going to take a trigonometric expression from an exercise from chapter 5.1 on page 379. Problem number 41 is sine beta times tangent beta plus cosine beta. So this is a trigonometric expression. Don't let the betas intimidate you. It's just a Greek letter, just like theta is a Greek letter. And it's used so sometimes to represent angles, sometimes they use alpha, sometimes they use x, but you should just think of it like an x. Okay. So the strategy they want us to use is to use the fundamental identities to rewrite everything, or in order to simplify this. And the first strategy that I would use is rewriting everything in terms of sine and cosine, because everything can be written basically as some form of sine or cosine. So what I'm going to do is the sine beta is fine. It's already written as sine. And then tangent beta, if you remember from our quotient identity, that's sine beta over cosine beta. It's one of our fundamental identities. And plus cosine beta, that's fine. Okay. Now, we've got a fraction in this expression, and whenever I have a fraction, I like to write everything as a fraction. That way it's a little easier to see sort of what's going on. So let's see if I can do this. Yeah, I'm going to kind of show you how everything is a fraction here. This sine beta, I can write that as sine beta over 1 times sine beta over cosine beta plus cosine beta over 1. So when we do this, it might be a little easier to see what's going on. And now I know if I'm kind of messing around with these tools, I'll use the highlighter here. If I've got a fraction times a fraction, right, I multiply the numerators, multiply the denominator. So let me do that. Sine beta times sine beta is sine beta quantity squared, which we write as sine squared beta, kind of putting the squared right by the sine there. And then 1 times cosine beta is cosine beta plus cosine beta over 1. And now we've got a fraction plus a fraction. And the way we deal with that situation is in order to add them, we've got to find a common denominator. So if we've got our denominators are cosine beta and 1, if we multiply them together, we get a common denominator, which is going to be cosine beta. So in order to achieve that, I've got to multiply this right term by cosine beta over cosine beta, which is essentially like multiplying over 1, or times 1. Okay. Now this is still sine squared beta over cosine beta plus cosine beta times cosine beta is cosine squared beta. 1 times cosine beta is cosine beta. So now we have the common denominator. Now I can actually add these two fractions. So I can write it all over the cosine beta denominator. And in the numerator, I've got sine squared beta plus cosine squared beta. Okay? And if you've done enough of these problems, you'll start to recognize expressions like what we've got here in our numerator. And anytime really you see a trig function squared in these kind of problems, it should be kind of a red flag that one of the Pythagorean identities is going to be involved. So here in this case, sine squared beta plus cosine squared beta is equal to 1. So I can replace that with a 1. Because I'm trying to simplify things, and that's a much simpler way to write that. So I'm replacing that with a 1, and in the denominator I still have my cosine beta. And then we can use another one of our fundamental identities, in this case the reciprocal identity. We know that since cosine beta and secant beta are reciprocals, 1 over cosine beta is equal to secant beta. And if I can write an expression as not a fraction, and I'm trying to simplify, I'm going to choose the not a fraction. So this is why this writing in a secant beta is a simpler form. And at that point, we've got it pretty, our job is pretty much done. We've got it pretty much as simplified as we can get. But maybe it might be sort of instructive to go back to the original and see what we started with. Sine beta, tangent beta plus cosine beta. That was our expression, and it's actually equal to secant beta, which is a much simpler form. All right.